And last talk of the session, it's an invited speaker.
Yes. So let me remove.
This is Grace Telford from University of Utah. She's going to talk about star formation in the low metallicity environments.
Okay, well, first I want to thank the organizers for inviting me to be here today, and also especially for working with me on scheduling what turned out to be a very complicated travel day. So very grateful to be here with you all to talk about star formation at low metallicity. So obviously, star formation is very important to the process of galaxy assembly, right? But feedback from short-lived, newly formed massive stars also is an important regulator of galaxy evolution. And we really need good models of massive star formation, evolution, and feedback at low metallicity specifically, if we want to understand things like how the baryon cycle operates in low-mass dwarf galaxies, or how early galaxies reionize the universe. And ideally, all of these models would be calibrated to spectroscopic observations of individual stars and gas structures in nearby galaxies that are very metal poor, where we can get those kinds of very detailed observations. But there's an issue with this, because among the star-forming galaxies that are very, very nearby, we can't really get below about 20% of the solar metallicity. That is what we can reach in the small Magellanic Cloud. But if we want to go to lower metallicity than that, to find galaxies that are still actively forming stars, we need to look much farther away at more like megaparsec scales. And so one target that is actually really great for this kind of work that is on that distance scale is Leo-P. This galaxy is just 3% of the solar metallicity, and it is the closest galaxy to us that is this metal poor and is still forming stars. And you can see the galaxy itself in this is a JWST near-cam image, so it's this cluster of blue stars here. And Leo-P is additionally special because it actually contains only one O-type star. So one star that is hot and massive enough to ionize hydrogen. And so it powers that only H2 region in the galaxy. So this is an unusually simple situation that actually makes Leo-P an extremely useful test bed for models of massive stars and star formation at very low metallicity. So for the first part of this talk, I'm going to focus on the portion of the baryon cycle where gas collapses onto galaxies, where it can then cool further and go on to form stars. At the end of the talk, I will also touch on the next phase where feedback from these newly formed stars can actually drive outflows from galaxies. So observations show us that star formation proceeds in cold molecular gas and dust clouds, which are dominated by mass by molecular hydrogen. But that observational statement is really driven by relatively metal-rich galaxies, more similar to our Milky Way. At low metallicity, the situation may actually be quite different. Essentially, the chemistry and cooling in very low metallicity gas is different, such that cooling times become much longer and the time scale for molecular hydrogen formation is longer than in a galaxy like the Milky Way. And so simulations that actually track all of the different phases of the ISM predict that at very, very low metallicity, star formation can actually occur in gas that is mostly atomic before molecular hydrogen has had a chance to form. So that is actually a really interesting statement, right? We need to understand if this totally different mode of star formation really is happening in low metallicity galaxies, because that would have important implications for the onset of star formation in early metal poor galaxies, and therefore when we should expect ionizing radiation to be produced in the early universe, right? So clearly we should go look in nearby very low metallicity galaxies and see if there is in fact molecular hydrogen in those star-forming regions. However, the universe is not always kind to us. Unfortunately, it's really tough to directly measure star-forming molecular hydrogen. So in cold gas, molecular hydrogen does not have any observational signature at all. So we are basically stuck using tracer particles to infer the presence of molecular hydrogen. And by far, the most common of these is carbon monoxide. So in Milky Way-like galaxies, this is abundant enough that we can very easily take observatories like ALMA and go find carbon monoxide emission and infer the presence of star-forming molecular gas. Now, in low metallicity environments, the structure of these molecular clouds actually changes quite dramatically. So essentially, low metallicity gas has less dust, and so that gas is less good at shielding molecular hydrogen from UV radiation. And molecular hydrogen and CO both dissociate when exposed to UV radiation, but CO does so much more easily. And so essentially, the CO cores in these star-forming regions are predicted to become quite small. There is a core there, you just probably can't see it on the slide. And so because they get so small, they are very, very faint and challenging to detect, even if there is a lot of molecular hydrogen actually present that we can't see, because cold molecular hydrogen has no electromagnetic signature. So even though it's faint, and this is probably a really challenging observation, we can certainly still try to find it, right? And a lot of groups have done this kind of detection experiment in low metallicity nearby dwarf galaxies that are still actively forming stars. And CO has been detected in a handful of these nearby dwarf galaxies to date, but in star-forming galaxies as metal poor as Leo P, this has remained quite elusive. And our team actually did an ALMA observation of Leo P and did not find any CO emission with that observing setup and exposure time, right? It could still be there, but we have not detected it yet. Now, this doesn't mean, again, that there is no molecular hydrogen there. There very well could be molecular hydrogen with just a very, very faint CO component or non-existent CO component. So we took an alternate approach, and I led a Cycle 2 JWST program to search for an alternative signature of molecular hydrogen in Leo P, using the MIRI MRS instrument to look for rotationally excited emission from warm molecular hydrogen. So this is gas that should be, just outside of the very cold star-forming gas, and would certainly indicate the presence of a colder phase of H2 in the galaxy if confirmed. And we actually did find this expected signature of molecular hydrogen from the warm phase in Leo P. So this detection, it is one resolution element, right? It is barely there, but it's right at the edge of the only H2 region in the galaxy. And this is exactly where we would expect the UV radiation from that only O star to be exciting the molecular hydrogen if there is a colder cloud nearby. So this is really exciting. It's the first evidence we have of molecular gas in a star-forming region in a galaxy this metal poor in the nearby universe. And I want to emphasize this was really weak. We were just able to detect this with MIRI MRS. Interestingly, the measured intensity of this line turned out to be exactly what we put into our exposure time calculations as a very, pessimistic estimate to make sure we got enough exposure time. So thank goodness we were a little on the cautious side there. But we do detect this H2S1 line. This is at 17 microns, and we detect it at the 5 sigma level, so we are quite sure there is this warm molecular hydrogen component in Leo P. But there are actually a bunch of different transitions in the MIRI MRS range, and ideally we would have detected many of them and then been able to measure the temperature and density of the gas. But we got non-detections on 2 of these lines. They're useful upper limits, so we'll come back to that in another slide, but there actually is one H2 transition that is all the way at the red end of the MRS range at 28 microns that was totally useless. The noise level gets so high in that part of the spectrum we really have no information about that. And unfortunately, that transition traces the coldest component of this warm molecular two-phase. So that was a bummer, but we ended up with good information that does constrain the physical state of this molecular hydrogen in LEOP. So this slide shows basically the two limiting cases that are allowed by these observations. In blue is a model. Okay, blue here is a model at basically the lowest temperature that we would expect to be able to produce this rotationally excited emission. And that model actually corresponds to a gas density that is comparable to what we observe for molecular clouds in the Milky Way. So that is interesting. But the data formally allow also for a warmer model, something more like 400 Kelvin, which would correspond to a density that is orders of magnitude lower. And that doesn't make a whole lot of physical sense, but would certainly mean we're looking at a very different kind of molecular gas than what we see in the Milky Way. Now, fortunately, we actually know a lot about the UV spectrum of that only O star that's providing the bulk of the UV radiation to excite this H2 emission. And that is because we have observed this star with the COS instrument on the Hubble Space Telescope. So here I'm showing you the UV spectrum of LEOP's only O star in black compared to a model that I fit to these observations in red. The details of that model are not important, but we have this information because I have been investing a bunch of my time in recent years trying to build up our observational data set of very low metallicity, massive O stars. This is the Treasury of Extremely Metal Poor O Stars program, or TEMPOs. LEOP is one of 29 stars that we have now assembled UV spectra of so that we can place empirical constraints on the physics of massive stars in this sub 20% solar metallicity regime. So this is pretty much the least relevant part of my talk to Roman, so I won't dwell on it, but if you're interested in this, please come talk to me at a coffee break because I'm very excited about TEMPOs. But the key point here is that we know what the UV spectrum of the O star in LEOP looks like. And so we were able to use this as the input UV radiation field in a model of the photodissociation region and basically show that there is no way to get the temperature in that gas cloud up to this higher temperature end of the formally allowed range. The modeling really strongly prefers the lower temperature scenario. So basically, we are able to say with high confidence that we are likely looking at a very cool, warm molecular hydrogen cloud, something like 80 Kelvin, which would correspond to a mass of about 10 to the 3 or 1,000 solar masses. And importantly, this warm H2 phase is definitely expected to be subdominant, right? There should be a much larger mass of cold H2 present in the galaxy, given that we detect warm H2 there. So this is suggesting that even this very low metallicity galaxy, which has very little evidence for dust, right? It must have a very low dust content, is still able to form quite a large amount of this molecular hydrogen. And so this is a useful constraint for models of the ISM and of star formation in very low metallicity galaxies, both dwarfs and high redshift galaxies. Now, Roman is about to give us a very complementary set of data for understanding star formation in both the Milky Way and in nearby galaxies, including dwarfs like LEOP. So Roman has, very high spatial resolution and will be in space. Its huge field of view and its sensitivity to infrared wavelengths, all of this together makes Roman extremely well suited for detecting embedded star formation and young stellar objects, which appear very red because the dust that is in their envelopes or disks, right? So by detecting young stellar objects directly, you can actually get a more accurate census of ongoing star formation than using traditional tracers like counting the much less common, blue massive stars, or even using H alpha, which is powered by only the most massive stars, as a proxy for the total star formation rate. In addition to detecting the YSOs themselves, Roman will be excellent for detecting resolved stellar populations in bulk, and if you have data in multiple filters, you can disentangle the stellar and dust components and basically create maps of the dust along the line of sight. And so that gives you a tracer of the star-forming ISM. And so Roman will definitely be able to provide new and exciting maps of the star formation process in the local universe. And I want to emphasize, in addition to being very good for tracing the star formation process, resolved stellar populations actually provide a lot of information about the impacts of star formation on the host galaxy's evolution. So I'm going back to this image of Leo P I showed you on my title slide, and you can see, again, this is a JWST image, so the individual stars are very easily resolved. And from this kind of space-based high-resolution imaging, we can measure photometry of those individual stars, and again, with data in multiple filters, we can construct color magnitude diagrams of the stellar populations in these galaxies. Now, by modeling the distribution of stars in this color magnitude space, we can actually back out the history of star formation and metal enrichment in the stellar population in this galaxy. And once we have those measurements in hand, we can actually use that to constrain the integrated impacts of stellar feedback on that host galaxy's evolution. And I think it's particularly interesting to do this for low-mass dwarf galaxies, because their shallow potential wells basically make them more susceptible to bursty star formation. And they are more likely to lose a large amount of their gas and metals throughout their lifetimes due to stellar feedback. Now, one way to observationally quantify the total impact of such stellar feedback is by measuring the fraction of metals that should have been produced by the stars in this galaxy that are actually retained inside the galaxy all the way to the present day. Now, I'm going to take a few minutes to just walk us through how we actually do that kind of calculation, starting from these star formation and enrichment histories that are measured from the resolved star color magnitude diagrams. So first, we combine these measurements with a model of metal production following a burst of star formation to calculate the total metal mass that should have been produced by various nucleosynthetic sources, different kinds of supernovae and AGB stars over a galaxy's lifetime. Then we use the same star formation and enrichment histories to calculate the mass of metals that is locked into long-lived stars that are still in the galaxy today. And finally, we need to combine that with a calculation of the metals that are present in the neutral gas and dust in the galaxy. And for that, you do need additional observations of the interstellar medium and a measurement of the gas phase metallicity. But so altogether, these two components give you a census of all of the metal mass that is inside the galaxy today. And the ratio of these two is the fraction of metals that has been retained. And so the implication is that the metals that are not inside the galaxy today have been ejected by feedback-driven outflows. And so today, we think they reside in either the circumgalactic medium or the intergalactic medium. And so recently, Christy McQuinn and I, along with a really great team of collaborators, have applied this technique to a sample of about 40 dwarf galaxies in the nearby universe. This is part of the GLOW project, or Galaxies Losing Oxygen Via Winds. And it is really the first empirical measurement we've had of metal retention in this mass regime between about 6.5 to 9.5 in terms of log stellar mass. And so what we find is that most of these low-mass dwarf galaxies retain less than 15% of the oxygen that should have been produced by the stars in those galaxies today. And interestingly, this is a lower retention fraction than is predicted by galaxy formation simulations that extend down to these low masses that are also able to reproduce the observed stellar mass metallicity relation and gas phase mass metallicity relation. So this is actually a really interesting new constraint on feedback in this mass range where simulations predict that feedback should have the biggest impact on galaxy evolution. And again, I want to emphasize that this measurement was made possible by a very rich archive of space-based resolved star imaging. And this is an area where Roman is poised to really dramatically expand our available observations. So I'm quite confident that everyone in this room has seen a version of this image, right? Where we have the Andromeda galaxy in the background here. So this image was assembled from hundreds of Hubble Space Telescope orbits where you can actually see the tile pattern, right? Right along, oh, this pointer. Okay, there's my pointer. You can see the tile pattern here. That is sort of the edges of the HST field of view. So this is many, many hundreds of individual orbits tiled over this huge on-the-sky galaxy, right? And it's a beautiful map. It's been so scientifically rich, but the point of this illustration comparing to the Roman footprint is that Roman could basically do the FAT survey, at least in the infrared filters, in just a couple of pointings. And so Roman is going to make this kind of resolved stellar populations work in very nearby galaxies much, much more efficient than it has been in the past. And it's really going to unlock our ability to do this kind of work. And I was personally very excited to learn just a couple of weeks ago that this very common illustration of M31 compared to Roman is going to happen. So Carrie Gilbert at Space Telescope led a really fantastic Cycle 1 program to obtain observations of both M31 and M33. And so this has been approved. We are going to get observations of M31 with Roman. And again, this just feels very right, considering how many times I've seen this exact illustration over the years. And it's going to be a really good demonstration of how Roman is going to perform with this resolved stellar populations work. So I look forward to seeing that data and what everybody comes up with in future Roman cycles. Okay, I will leave my conclusions here, and I'm happy to take questions. Thank you all.
Okay, thank you very much for a great talk. Questions? Right up there.
Thank you very much for a very interesting talk. I was wondering if you have measured the dust for the LEOP, and by dust I mean, for example, from the Balmer decrement, the Balmer line ratios, measuring the dust for LEOP?
Yes.
And if that is in agree with like zero dust, considering like K-speed recombination, or is it below the ratio that we expect from K-speed recombination?
It is essentially in agreement with zero. Okay. Like the uncertainty on the measurement is consistent with zero. So I cannot say for sure that there is a detection of dust in LEOP, but it is something we are continuing to work on with the MIRI data we have in hand. Stay tuned. I hope we are able to detect some dust, but not yet.
Okay, thank you.
Okay, other questions? Let's see. Maybe right here.
Really exciting talk, and I'm so excited about the General Astrophysics Survey. I wanted to ask, if the oxygen is so much lower than what had been predicted, does that have implications for other species that might also be lower than expected?
Yes, that is a really good question. So, okay, there are different approaches taken by different authors who do this kind of metal retention work, right? Like, you can basically either say, I'm going to try to calculate all the metals that should have been produced and all the metals that are present today, or you can pick one species to focus on that you think is a little more reliable to measure. And so this particular study focused on oxygen because we do just measure the oxygen abundance in the gas. And for, let's see, oops. Oh, no. I'm very sorry, I lost the pointer. I just want to go back to that slide.
This one?
Yes, thank you. Okay, so for these galaxies, so we have it broken down into stars, gas, and dust. You can see it's mostly gas, right? And so that comes from the H1 content of the galaxies combined with the gas phase metallicity or oxygen measurement. So we stuck with oxygen because that is the dominant reservoir in this case. So I hesitate to say anything about other elements because that is what we focused on, right? I would assume that other elements that are dominated by type 2 supernova production follow a very similar trend, but I can't say anything confident about other nucleosynthetic sources because we only worried about oxygen here. Hope that helps.
Is the offset you see in the molecular hydrogen detection consistent with like an enhanced density in the H2 region?
The offset.
Because it
Like,
seems
do you
like
mean
it's slightly
spatial?
offset to the top right-ish of the...
Yeah, so I do think that's what's going on, actually. You know, I don't even need to go all the way back to that. You're right, the H2 detection was up to sort of the upper right, and if you look carefully at this image of the H2 region, you can kind of see it looks brighter up in that upper right corner. I do think that there is a density enhancement there, and, you know, this is speculation, but a picture I think is realistic is that there's probably some cold H2 up here, at least at a higher density than in another portion of the galaxy. So it would be sort of, you know, an H2 region that's on the edge of a gas cloud. But again, can't prove that with actual data. It's just, it hangs together.
Okay, thank you very much,
Great,
Grace.
thanks.
Let's give all of our speakers a good round of applause.